drug-based reasoning explainer, a framework that we developed to provide interpretable drug repositioning explanations. And I just want to briefly start saying that our project is motivated by the current challenge of developing new drugs. As you can see in the figure, traditional drug discovery takes a lot of money and a lot of time. And I think what is more concerning about these traditional approaches is that bringing a new drug to the market, only few initiatives will actually be successful. So there is a lot of interest from the industry to develop novel strategies. So drug repositioning is this idea of taking drugs that are already approved and that are already out in the market and find new uses to them. And by using biomedical knowledge graphs where we can integrate a lot of information from the scientific literature or the biomedical databases in one place, we can analyze the drug mechanism for multiple drugs and then predict novel connections with a disease that currently lack a treatment. But how exactly do we leverage this information in an efficient way so we can make such predictions? So using graph neural network models, we can basically create a simpler representation of our graph in the embedding space, where the idea is that those nodes that have similar connections or share a similar neighborhood should be ended up close together in the embedding space. And so for our task, what we expect to see is that drugs that treat a disease with the same mechanistic path should be ended up close together in the embedding space. And then following this principle, we can identify novel connections with diseases that have similar connections or similar mechanistic paths with drugs that we already know that they treat certain diseases. So this is great, and I'm probably oversimplifying how exactly GNN works and how this scoring function works, but the main point is that most of these graph neural network models do great predicting connections between two nodes, in this case, a drug and a disease. But what they are missing and what is really important for domain experts to make better informed decisions is to understand what is the biological rationale, what are the sequence of nodes and edges that explain the prediction that we're getting from these GNN models. So having this challenge in mind, we develop a framework that not only predict novel connections between drugs and diseases, but also provide these explanations so we can understand our predictions. So I introduced to drug-based reasoning explainer. This is a case-based reasoning strategy that uses a GNN framework to make these predictions. As you can see, we have two main modules, the link prediction module that create these novel predictions and provide the explanations, and the important paths modules that rank the most important paths that we are getting from the link prediction module. So I will dive into how exactly the link prediction module works. We're using a case-based reasoning strategy. And for those that haven't heard about case-based reasoning, this is an old artificial intelligence framework that was developed a long time ago. And the main idea is to learn from past experiences. And I think a really nice analogy to understand case-based reasoning is to think about how we usually face new problems. For instance, we can think about a chef that he's trying to create a pasta dish, but he doesn't really know the recipe. He might need to think about what he has done in the past, think about the ingredients, think about the techniques that that have worked for him, and use that knowledge to create the pasta that he wants. So the same way, case-based reasoning try to use similar experiences that work in the past and use that knowledge for a problem that it's trying to solve. There are three main step process. So we have retrieve. So given a new problem, we first need to retrieve similar cases. We reuse the solution from these similar cases. And then finally, we need to revise if those solutions were helpful for our current problem. So for drug-based reasoning, the framework that we developed, we are following the core idea of case-based reasoning. So the task here, again, we have a drug and we want to predict a novel connection with a disease. And we follow the core idea of case-based reasoning. We have a drug, and we first retrieve similar drug cases. We perform a nearest neighbor search. We look at the mechanistic paths in the knowledge graph. And then when we take these mechanistic paths and use it as a template for the problem that we're solving, we ended up arriving to multiple disease candidates that can be repurposed. And then finally, we need to revise which of these ones are more likely to be repurposed. So this is just an overview of our framework, but I would like to go into a little bit more details of how exactly this model works. So yes, and for this, I'm going to use a simple example. Propanolol. Propanolol is a drug that is currently approved for hypertension. And the question here is, can our model predict hypertension as the true answer? And can we predict other novel candidates for propanolol in this case? So again, the first step is to retrieve similar drug cases. We perform a nearest neighbor search. And as you can see, the top predictions that we're getting are also treating heart-related issues such as acute coronary syndrome, pulmonary hypertension, and so on. And this nearest neighbor search is done in a very simple way. Essentially, all drugs that we have in our knowledge graph are parameterized in a simple vector representation that represents the outgoing relations that we have in the knowledge graph. So the size of the vector is going to be the size of the number of relations that we have in the knowledge graph. An entry set it up to 1 if the relation exists, 0 if it doesn't. You do the same for all the drugs, and then by simply calculating a cosine similarity, you get the most likely similar drugs. So the intuition here is that drugs that have similar relations in your graph are going to end up together in this cosine similarity score. And the idea is that if they're sharing relations, we can use the relations in their knowledge graph for the problem that we're trying to solve. So once you define your nearest neighbors elements, you look at the solutions they're using. Over here, I'm just showing one example. The first example, clopidogrel help for acute coronary syndrome. And you look at the paths on your knowledge graph. Over here, I'm just showing 2 paths, but you can decide how many you want to look. And then the idea is to look at all the paths for your nearest neighbor entities and generalize them into meta paths. And the idea to generalize them is to make it more usable for your problem, right? So once they're generalized, you can go back to your problem, in this case, propanolol, and use them as a template to start exploring your knowledge graph. So when we do that and we explore the knowledge graph using these templates, we ended up arriving to possible solutions, including the correct answer, hypertension. But naturally, these templates can lead us to incorrect answer or less likely answers that are likely to be repurposed for propanolol, like bacterial infection, for example. So the last step is to revise which of these connections are more likely to be repurposed. So we train our model following the idea of case-based reasoning, where similar cases should have similar solutions. So we have both the subgraph from the similar entities and the subgraph for our query, propanolol. And we train a GNN model such as the embedding for the correct answer for the similar cases, the acute coronary syndrome, and the representation for the correct answer that we know is true for propanolol should be ended up close together in the embedding space, because we know that are true. And then incorrect answers such as bacterial infection should end up together far from this embedding region. And so this idea will allow us to identify Parkinson as a possible answer, because as we can see in our graph, it's sharing mechanistic paths with hypertension. And this idea can be formalized, or this training process can be formalized as maximizing the similarity of correct answers and minimizing the similarity of incorrect answers. All right, so that's basically the details of how the link prediction works. And again, we have access to predict novel connections between a drug and a disease. In this case, the example that I'm showing you, I'm just saying that propanolol was predicted for Parkinson's disease, which was actually really interesting because propanolol was first indicated for hypertension, and then in the 60s, I believe. And then later on, it was repurposed for tremor symptoms. And we know that one of the main symptoms for Parkinson is tremor. So, but yeah, now we have access to look, and we can look at the paths that explain this prediction. We do see that there are some genes that are connected to tremor and how tremor is associated with Parkinson's disease. We also see that the same gene is associated with some inflammatory processes, and there are other genes that are also connected to this inflammation process that is related to the Parkinson's disease progression. So this is great, and domain experts now can understand and go back to the lab and test if this is actually true. And this is great, right? So, but now the next thing is that I'm only showing you 3 paths, right? But the reality is that we have access to a lot of paths that explain these connections. It can go to 100 paths depending on the query. And of course, this is really challenging and really time consuming. We need to identify which of these connections are more relevant for the prediction. And so for the second module of our framework, we introduced to the important paths module that basically takes the set of paths that we identified on the link prediction module and rank them based on importance. And for this, I just want to mention that, and we know that graph neural networks are basically black box models. We don't really understand why they make certain predictions. Like in our case, we have propranolol treating Parkinson. We take it to your GNN model that you train, and you know that they are connected by a certain probability, but you don't really know why, right? So the graph community has been really interested on developing explainable models that allows you to identify the most important connections. So in our case, we want to identify which of the connections that we have are explaining this probability that we are getting from the GNN model. We use a perturbation-based approach. The idea of using a perturbation approach is that you do small changes, you perturb your graph and see what happened to your prediction. And so what happened is that you remove something from your graph, like let's say that we remove the connection between the beta-adrenergic gene and the tremor, and you evaluate what happened to your original prediction. So let's say that you remove this from your graph, from your subgraph, and you pass it through your GNN, and you see that there is a drop in the performance, meaning that what you removed was actually important, and you shouldn't remove it, right? So perturbation-based models iterate multiple times to the graph until it finds the correct, until it finds the minimum number of components that keep your original prediction. So let's say that we iterate back and we remove inflammation and cytokine regulation. When we take it back to the GNN, we see that we keep the original prediction, meaning that we have found the minimum number of connections that are required to keep the prediction that we got previously from the GNN. And this idea of removing edges and keeping edges can be formalized as learning an edge mask, which means that you assign a score to all the edges that you have on your subgraph, and you learn these scores, which 1 means more important, 0 means less important, by minimizing the probability from your original prediction and the one that you're getting when you're perturbing your graph. So once we identify these important connections based on this minimization, we were also interested on selecting edges that form meaningful paths, meaning that we want to focus on nodes that have a balanced connectivity. In biomedical knowledge graphs, we usually deal with nodes that are highly connected, like P53, and P53 is basically related on all type of cellular processes, and it's not very informative when you are trying to explain something. Or then you have like isolated nodes, like non-coding RNAs that no one knows a lot about it. So it's also not adding a lot of context to your predictions. So you want to ignore that. And for this, we introduce a simple node degree penalty that basically measure how far the connectivity from your graph, how far it is from this optimal value. And this optimal value is something that you learn. And basically, those nodes that are close to this optimal value are less penalized, and those that are far are going to be more penalized. So in this case, we can see that the nodes that I have over here that are close to the optimal value do not get penalized, and then inflammation and cytokine regulation get a little bit more penalized because they're far from this optimal value. So once we define the edge scores and the node degree penalty, we can score all the paths that we have in this subgraph. And for this, we introduce this path score that basically takes into consideration both the mask edges, the mask weight that we learned from the previous slide, and then this node degree penalty. So you basically assign a score to all the paths, and this path score is going to ensure that those paths that have edges with important weights and edges that were less penalized going to have better scores than those that were not important for your model and also were a little bit more penalized. And then basically you define a threshold of what do you want to select as most important paths. And then that way you have your list of important predictions that explain the connection between a drug and a disease. And then lastly, I just wanted to show you that once we defined this framework, we were really interested on evaluating if the actual paths that we were getting from our model were actually true. So we use this DrugMechDB. This is a knowledge graph that we built in our lab that basically integrates mechanistic paths. We integrated around 5,000 mechanistic paths that were carefully curated by domain experts, so we trust them, and we use them as a gold standard. And so the question here is whether our model, our drug-based reasoning model, is able to find these connections as true, right? So what I'm showing you here is basically comparing our model against other explainable models, and the hit rate is basically calculating the proportion of correct answers from DrugMechDB that were able to be found by these models. And as you can see, the blue line shows that our model is outperforming better than the other ones. And it was really impressive to see that by the 100 ranking, our model was already able to find 40% of the correct answers coming from DrugMechDB. And then the ROC metric is just basically setting up different thresholds for your mask. And as you can imagine, defining what is important and what is not important depends on what threshold you set. So with this metric, we still see that drug-based reasoning explainer is outperforming all the other explainable models. And I just want to briefly summarize how our framework works. Again, we have two main modules, the link prediction modules that uses a case-based reasoning strategy. We first need to find similar drugs, use the mechanistic paths that we have in our knowledge graph, and then based on this, we can derive novel connections, and more importantly, we have access to the mechanistic paths that explain these connections. And then the important paths modules take this subgraph that we derived from the case-based reasoning approach, and by using this perturbation-based approach with a no-degree scoring function, we are able to find the most important connections in a ranked way. And I think this is one of my last slides. I just wanted to say that this is available if people want to use it. I think the slides are going to be available as well later on. So yes, and then I just want to acknowledge my mentor and all other collaborators that make this project possible. And I think that's basically it.
Do we have any questions from the audience? Oh, perfect.
Real quickly,
Well, you do. Virtual people, they have to hear you.
sorry, virtual people. Can you say a little bit about the graph models you were building and those relationship types in there? Because I saw like part of, associated with. Have you guys tested using different kinds of relationship types in terms of the retrieval accuracy of those models? Because I know sometimes the overuse of something like associated with gives you a lot of hits in graphs because a lot of things are associated with inflammation.
Yes.
That are not Parkinson's disease. That could just be an injury, an arthritis, lots of things.
Yes.
So do you have anything else you can expand on some of your relationship labeling in the graphs?
Right, yeah. So the knowledge graph that we're using is something that we built in our lab. We integrated multiple databases, and yes, we do have those kind of relations that can be a little bit too general. And I guess that's why the second part of the project was to how do we deal with that? And I think considering the connectivity of the nodes kind of help us, because as we can see on the results, we do perform well with the true paths. But yeah, I think we have talked about that, like how do we improve our knowledge graph? How do we make it a little bit more, with a little bit more context, right? And instead of only saying, hey, this is associated, maybe just add more information. And I think that can really improve the results. But yeah, for now, this is what we're working with. Yeah.
Great. Any more questions? No? All right. Well, thank you.